Hello. This is a project that began during my first semester of graduate school when my advisor asked if I wanted to help NASA fix a space robot. Of course, I said yes, packed my bags for Houston, Texas, and began working with Robonaut2. Robonaut2 is a dexterous humanoid robot that was deployed to the International Space Station, and it uses its human-like dexterity to make use of the existing tools and infrastructure that were all designed for human astronauts. Using the existing infrastructure allows Robonaut2 to automate dangerous, time-consuming, or difficult tasks without needing those specific tasks to be reconfigured for automation themselves. Robonaut2 is eventually outfitted with legs, and you can see here that it takes up most of the space in a space station compartment. So it's very important that the robot be able to respond to changes in its environment, be able to bump into an astronaut or a misplaced piece of equipment without causing damage. Robonaut2 accomplishes this with a set of series elastic actuators where each motor is connected to whatever it's driving via a spring. And by sensing the deflection of that spring, the robot senses very precisely how much force it's applying. And if it's applying more than it expects, it can stop motion very, very quickly. This allows Robonaut to pick up objects at its maximum mass weighting, but still be stopped by a human putting their hand lightly in its path. These safety features are what allow Robonaut2 to work in compartments like this without exclusion zone safety cages or other e-stop equipment that you would see in like a factory setting. But during its deployment, a new problem was seen where one of the position sensors used on those series elastic joints would initialize 60 degrees off its actual location. The flight control computer would see this as excessive force on the joint and prevent the joint from being unsafe for motion. Thankfully, this only occurred during initialization of the joint, so the robot wouldn't stop in the middle of a task, but it could get locked up while trying to engage it in a new task. This was a hard fault all the way down at the lowest level of the sensor and motor controller, and at the time, it was not replicated on the ground. At the time, mitigation required either a member of the ground team or an astronaut to diagnose the faulty sensor manually. This was a time-intensive and expensive process. We were asked if we could automatically disambiguate the faulty sensor, both to save them the time of diagnosing it initially and to enable future automatic mitigations of the problem. Some additional constraints: we were asked to embed this solution directly on the motor controller, specifically on a field programmable gate array or FPGA, both because this is what had the most resources available, but also for concerns regarding software certification of the microcontroller actually running the motor control loop. As an additional caveat, we were asked if it would be possible to make whatever solution we came up with reconfigurable without resynthesizing the full FPGA. Resynthesizing FPGAs can be much slower than compiling software, and deploying them, especially in space flight, is not desirable. The real-world complexities of this project made it more interesting than a textbook runtime verification application. We were required to write and prove correct new temporal logic observation algorithms, back them with a new data model, shared connection queues, and implement common sub-expression elimination on the input formulas to fit the specifications we were interested in onto the available FPGA fabric. This is really leftover space that wasn't intended to be used and only happens to exist on the part in question. At the end, we were able to accomplish running RV tool on Robonaut2's motor controllers, specify the fault disambiguation case in a way that produced no false positives or false negatives on any of the available input traces. And in that case, the common sub-expression elimination was required to get this formula set running on the robot. So it demonstrated its usefulness there. Our solution is online, stream-based, real-time, reconfigurable runtime verification. And looking around at all the tools that can do the various components we need, run in hardware, be reconfigured at runtime, the one that was closest to what we needed was RT2. The RT2 runtime verification framework was designed specifically for flight systems. and as a key design decision, made its hardware implementation reconfigurable at runtime as opposed to at synthesis time. These were two of the most important features for us because they got us the closest to this end goal, even though no tool did everything we needed and fit on Robonaut2's motor controller initially. RT2 supports temporal logic specifications written in mission time linear temporal logic, which gives finite integer bounds on the temporal operators. This specific fragment of temporal logic was expressive enough for us to talk about the behavior of the system over time without being too expressive that we were paying for it in performance and resource consumption, which we were already tight on to begin with. So the goal for the fault specification was 100% detection without false positives and disambiguating between the three cases if the absolute position sensor on the motor side of the actuator was faulting, the APS on the load side of the spring of the actuator was faulting, or there is no fault, which in this case also means some system fault that is not of the 60-degree initialization offset type. Determining a fault strategy was not perfectly straightforward. It required synthesizing data from various debug levels and bus versions from both the space and a similarly faulting ground Robonaut2 unit, as well as discussing the fault with subject matter experts on the Robonaut2 team. But we were able to come up with a fault strategy where we look for a large discontinuity in the report position of the joint and blame the absolute position sensor that jumped at that discontinuous point. So we're assuming that that discontinuity is the fault signature itself, which is borne out by all the data we have available. And we're also assuming that only the faulty APS moves at that discontinuous point. We believe this assumption is safe because this fault only occurs when the robot is already in a safe and lockdown mode. So the absolute position sensors actually aren't physically moving. This is the RT2 configuration for our specification set. We pull in three values from the sensor bus: the reported position of both absolute position sensors, as well as the reported position of the motor's built-in encoder. The signal processing layer then converts these values into Booleans for use by the temporal formulas. This E value notes if the encoder position is well out of range, which is a signature of the fault discontinuity. We then have 6 subformulas, A0 through 5, referring to the position of absolute position sensor 1. We kind of imagine dividing up the range of the actuator into 6 segments, and these Booleans tell us which of the 6 segments the position sensor is in. We have another 6 of these for APS2, and then we can write our temporal formulas to specify the fault as saying if you have APS1 in segment N and the encoder is healthy, and then in 1 to 2 time steps, that absolute position sensor is no longer in sector N and the encoder is unhealthy, then we state that that absolute position sensor is faulting. So there's another 6 of these formulas for APS1 for a total of 12 temporal formulas, stating that at the same time range that the encoder went from healthy to unhealthy, this absolute position sensor moved between these segments. Since these segments are sized such that there's no way to move the 60 degrees that is seen in this fault case without moving at least one segment over, this has proven to be both sound and complete over all the available trace data we have and some simulations. This observer tree shows how the data bubbles up from the bus values through the signal processing layer to the 12 temporal specifications. As I've mentioned, we get no false positives or negatives on all the recorded data as well as our simulated faults. But unfortunately, this specification was initially too big to fit on the available FPGA space. It uses 154 internal RT2 instructions. I'll explain more about those in the next section, as well as 140 of those shared connection queue slots. 140 shared connection queues with a total of 196 slots. But when we implemented the common subexpression elimination that I'm about to explain, we were able to reduce the instruction size by about a third, which correlates directly to speed, and also reduce the memory usage by about 28%, and crucially reduce the address bus of those queues by 1 bit. And that was really what made us come in under the line to fit on the restricted space. So let's talk about embedding the RV on that restricted environment. This is the mental model we went into the project with, that we would stick some sort of observer on the FPGA where it could listen in to the sensor pre-processing and the bus communication. The FPGA handled all the comms between the various sensors coming in from this bus down here, as well as the commands out to the actuator, and that we would compile our formal specifications through and load them into the observer through some other channel, giving us that runtime reconfigurability. Now, resource constraints for FPGAs are a little interesting if you haven't worked with them before. These graphs are outputs of our internal tool chain for determining RT2 resource requirements. And we're currently parameterizing over timestamp width, which is kind of the maximum temporal window RT2 can reason over. There's a number of other parameters that affect the scaling as well. This top graph talks about number of lookup tables. That you can think of that as kind of raw logic on the FPGA, and you see that we scale linearly, but the scaling itself depends on the actual type of FPGA. That's something to be conscious of. And you see here in the use of BRAMs or block RAMs, this is on-chip memory of the FPGA, and you see this is highly nonlinear, and a lot of these jumps are caused by bus widths. So when we talk about 18 kilobits of BRAM, it'll be of a certain width going in. If you need more than that, you're using 2 lines at a time, or you have to have custom wrapping logic. And this is one of the reasons why the ability to shrink the address bus by that 1 bit was so significant in making sure we could fit our new specification on Robonaut2. So RTU2 uses a formula decomposition as opposed to an automaton structure for formula evaluation. This is what gives it hardware reconfigurability without resynthesizing. So if we have this sample formula, not always from 0 to 3, A0, some input sensor, until from 0 to 5, always from 0 to 3 of A0, it breaks into a tree like this, where the values propagate at the bottom. There's these holding queues between the various nodes of this tree, and the engine goes through and executes each node, taking input from the queue behind it and pushing output to the queue above it until it bubbles up to the top and we retrieve our verdict. Now, you may notice that these 2 parts are identical, the always 0 to 3A0. And if we can find a way to share the output so we only have to compute that once, that is our common subexpression elimination. So here I have labeled the abstract syntax tree corresponding to that same formula, highlighted the same segment on both legs of the tree, and showed how they would share the data output, which means we need a different model for that queue. The RTU2 native data types cannot handle this. There are strong assumptions about queue depth related to single operator parents. That's where we came up with shared connection queues. They're single writer, many reader ring buffers that sit in between those parts of the abstract syntax tree and allow for the readers to be multiple parent nodes across the tree. In memory space, we take a strip of memory and set read, write, and wrap pointers at initialization time, allowing us to resize the queues as we reason over different formulas, preserving the runtime reconfigurability of the engine. To look at the impact of adding this in, we ran the CSE optimizing formula compiler over a benchmark of 10,000 randomly generated MLTL formulas. We see about a quarter size reduction of the abstract syntax tree itself, which most directly correlates to speed. A significantly smaller percentage, more like 1 or 2%, reduction in total memory necessary, because the bulk of the memory needed is going to be by 1 or 2 nodes that have a really high latency between when they're produced and when their parent node can use them. And sharing cuts off the need to keep the smaller of the 2 durations available. So we see this relatively small savings, although every little bit of memory savings is significant, and we have found this number to be much higher with human written formulas than random formulas. As you saw, the numbers from our case study in particular bear that out. So our final implementation, we ended up putting RT2 on the FPGA and sitting between that internal sensor bus and the shared RAM interface that allows the flight computer to probe values directly if necessary. And by sitting in on that communication, we were able to read all the sensor values as soon as they were available without impacting the timing of the sense control act loop that was critical to maintaining the existing functionality and certification of the system. This is an example of the system's output. We see this top chart showing the values of the encoder position as well as the joint torque computation from the spring deflection over time. We've been applying some light friction to the joint, so it's fighting against that as it goes through these commanded motions. And when we get over here at about time 200 seconds, we'll really start torquing on it to see the impact of an external force. Down at the bottom, we have a series of increasingly complex reasoning activities. We start off with simple comparison, encoder position greater than 1 radian. As we move on, we show propositional Boolean connectives, basic temporal operators, and we can even do nested temporal specifications, reasoning live over this data stream. I'd like to show a little video of it in operation. This video is available on the website that I'll have a link to at the end of the talk. And we can see on the left side here, we have the output of RT2 showing the output of our various formulas. In the center is that script chart showing the values live from the robot. And you can see a member of our team manipulating a knee joint sitting on a test bed. And you can watch the difference in the position sensors as he torques it away and then lets it rest back towards the center of that spring value. Of particular interest here, we rewrite the specification and redeploy it all without stopping the robot. Not only do we not have to reprogram the FPGA, but we don't even have to stop the control system going to the reconfiguration mode of Robonaut2 itself. We can just tell R2U2, please reason over this specification instead. So in ongoing work, we're going to continue adding R2U2 units across the networked joint controllers and start distributing specification amongst them, and potentially add R2U2 reasoning engine at the flight computer level to integrate reasoning results from all the subordinate controllers. And we have a number of additional uses for SCQs beyond the common sub-expression elimination we're exploring. We're going to continue to try to answer questions about efficiently incorporating these temporal monitors into live running systems. It's said that no plan survives first contact with implementation, and this project provided an opportunity to explore the gap between the theoretical solved portions of runtime verification and what is actually needed when you go to implement it, especially on an existing system with a retrofit. We were able to design new MLTL observer algorithms, new memory model, and add new optimizations to take what we thought would be an off-the-shelf solution and tailor it to be able to operate in this unique environment. At this point, I'll take your questions. Thank you.